Yes. Hello.
Yeah. Actually, we have many participants, so we will host the whole program in YouTube. Okay. So in
Okay.
Gmeet, only session host and session chair will be present. So
Okay.
after your speech, session chair will take the question from YouTube and will deliver to you. Okay.
Okay.
Mhm. So just 1 minute, we will start the live. Sajal sir, please tell when the live will start. Okay, start.
May I start, sir? Modak, sir?
Yes,
I am
madam.
I am audible, no?
Yes, madam.
Okay. A very good afternoon, all of you, and a warm welcome to the first day, second session of the International Faculty Development Program. Myself, Dr. Rakhi Bain, Associate Professor of CSC Department of BCET Durgapur. I am the host of this session, and Dr. Sankar Mukherjee, sir, is the Professor of CSA department is the session chair of this session for today. Now I like to introduce our resource person, Dr. Debasmita Bhoumik. Dr. Debasmita Bhoumik presently serves as a research scientist at IBM Quantum and also a senior research fellow at Indian Statistical Institute of Kolkata. Dr. Bhoumik has also industry experience as research intern at the IBM Quantum. She have also the academic experience as a assistant professor at Sister Nivedita University and a guest lecturer at Ashutosh College. Dr. Bhoumik achieved the gold medal from the Bethune College. She secured the first position as a and the first rank from the University of the Kolkata. Now I warmly welcome to her. Please, ma'am, share your valuable speech with us. Please, ma'am.
Hello. Let me first share my screen. Just a moment. Is my screen visible?
Yes, ma'am, it is visible.
Over to you, madam.
Yes. Just a minute. Uh, can you? Yes, okay. Yeah. So, good afternoon, everyone. I am Debasmita Bhoumik from IBM Quantum, and thank you to the organizers for organizing this nice FDP. And today, I'm going to talk about the very popular buzzword kind of thing that is happening, that is quantum machine learning, because both the quantum computing and machine learning are currently a very hot research field right now. And the the main goal of today's talk will not be uh, how to use QML. Of course, we will go into that. It is a 90 minutes talk, right? So we will try to cover some hands-on, like how do you can implement quantum machine learning. But my main goal will be uh, to deliver the message that where we shouldn't use quantum machine learning, because whenever we see some research papers coming out, be it as the reviewer or be it as any in any collaboration with any institute, uh, a lot of time, not 100% of the time, a lot of time we face the issue that the same problems that we can solve with machine learning, like the projects students usually do, like image classification, brain tumor classification, handwriting recognition. There's those common, very popular ML tasks in which classical ML is really good. We see that people easily reproduce those those classification tasks as the data is available and everything. People do it in machine learning, and people do it in quantum machine learning, and then they compare. And of course, sometimes quantum machine learning gives better results, and they publish it. Now the thing is, if it is giving better result, then why not? Because like what I am trying to convey is, we shouldn't do that. That whatever we are doing in ML, like handwritten writing recognition or brain tumor recognition, we shouldn't, in the research aspect, not learning aspect. While learning, studying, we do a lot of things, like toy problems or stuff. But while we are doing research, we shouldn't do that. Why? Because quantum computing itself is a very costly process. Now, suppose we will come into these topics again and again in today's talk, but I'm just trying to set the ground that what will be the actual focus of today's talk. So, suppose in a brain tumor detection or handwriting recognition, our classical ML is doing so good and it is giving you 98.5% accuracy. I'm just giving some random numbers. It's not that I'm citing it from some paper. Suppose it is giving 98.5% accuracy. You run the so there are already many ready-made packages of quantum machine learning. You run that and you get 99% accuracy. So you get 5% more accuracy. But with the confidence level with which you say, okay, the previous result of classical ML is correct, it's just 0.5%. It won't differ much, but it will be so much costly. So in a research point of view, it is not what is something needed to be done in quantum computer. Quantum computers are not for that kind of work. You can do, but it is not valuable for you. Like you are paying a lot and it is really not needed. So what we will try to understand is the reality check. Before building, we should understand the limitations, that where we can use and where we can use, but we shouldn't. That difference, that will be the goal of today's talk. So we are going to be honest about when quantum machine learning works, when it doesn't, and most importantly, how to make that decision by yourself. Getting a problem, getting an application, be it from which domain, be it CSE, be it AI, ML, electronics, physics, chemistry, bio. Every researcher have their own domain, own problem statement. By looking at the problem statement, you have to decide. There are techniques to be practiced by which you can make the decisions, but you have to decide that will QML be apt for this, or there can be other techniques. which will be less costly. So by the end of the today, I will try to give you some hands-on experience on Qiskit. By Qiskit, you can use QML in your hand for toy problems and also for research problems, and you will understand the bottlenecks that limits the quantum machine learning in production, at least till now. So let's get started. This is our agenda. And first, we will cover the fundamentals like what is machine learning, what are the kernels, what are the key misconception about QMLs or quantum's exponential parallelism thing. Then we will dive into why quantum matters at all. I know quantum may be a new topic for many of you today, so we will dive into a little bit of basics of quantum, uh, and then we will go into the quantum kernel, like the quantum version of machine learning. We will little bit touch into variational quantum classifier, that is a good QML algorithm. We will see some data encoding strategy because that is the most important part, but the maximum of research scope is there. That you have a problem in your hand, that means that is a classical problem in most of the cases. All the real life problems we want to solve, be it a medical problem, be it a calculation problem, mathematical problem, all the problems, if you think about it, it's classical problem. Then how to get the classical data into quantum or qubits, that is the data encoding, we will get into that. And how to build the variational models like the QML models, and how to extract the labels, so if it's a classification thing, and optimize them. And finally, we will ask the critical question, that is this even advantageous? And then we will see some little bit of coding so that you can, it's not as you have to follow along or do coding right now. I will give the materials, you will try at your home at your own pace. And if there is any question, the host can interrupt me and ask. That's fine. So let's start with the overview and motivation. These things we already know, I think, but let's just recap with the basics, that what is machine learning? Machine learning is basically a subset of artificial intelligence focused algorithms that learn some patterns, that learns from patterns from training data, and it makes prediction on new data. Now we have two different types of learning. One is supervised learning, where we train on labeled data set, and another is unsupervised learning, where the algorithm basically finds some patterns in the unlabeled data set. Now the key concept here is kernel, because what happens in classical machine learning, we often map low dimensional data into higher dimensional data, the higher dimensional space, so that it makes easier to draw separating boundaries. So in quantum machine learning, we basically want to leverage, there is a concept called Hilbert space, we will come into that, but we want to basically leverage the quantum Hilbert space as that higher dimensional feature space. So basically, in classical, we do this kernel method for lower dimension to higher dimension. That thing is done in quantum, really using the quantum Hilbert space. And the hope is that quantum entanglement, quantum superposition, those physics properties or quantum mechanical properties can capture the correlation that sometimes the classical kernel needs. So sometimes is important. So there are some tasks where these classical kernels cannot correlate the features. In those cases, quantum can help, but this is too crucial because the success that, okay, we used quantum machine learning and it is successful in a proper sense, basically depends on, first is careful data selection, and so on which data you are running it, and some novel quantum feature maps, like what features you are selecting. It's not that, like it is not advisable that we will blindly download any data set from Kaggle and apply some QML algorithms to it and get some result. So we all know that in classical machine learning, low dimensional feature space to high dimensional feature space is needed for better separation. So if you see the picture, that there are some red dots, outside there are some blue dots, and you can draw a line. You can draw a circle kind of thing, but you can draw a line or a plane. So how to draw a plane? If you break them into 3D, so it was a 2D picture. The first picture is a 2D picture. If you break it into 3D, then you can pass a separating hyperplane. This is the concept of our regular kernel. So in quantum machine learning, we basically map this to quantum Hilbert space. Now, these are new terms, I know, but eventually we will get habituated with the terms. Um, so in quantum, instead of bits, we deal with qubits. Qubits is, I will again come into the details of it, but qubits is a thing which can be at a time into 0 and 1. This is a very crude version, not a mathematically perfect definition I'm saying, but bits can be 0 or 1. Qubits can be in a superposition of 0 and 1. So with n qubits, we can get up to 2 to the power n dimensional space. So what happens is, if we simultaneously can be in 0 and 1, so with n qubits, we can get access of 2 to the power n dimensional space. 2 to the power n means it is exponentially large. So the hope is quantum entanglement captures the few correlations that classical kernels miss, because classical kernels dimension space is not that high. Okay. So basically this quantum feature map is the most active research area right now. Like most of the open problems exist in this quantum feature map, and mainly in quantum feature map and quantum data encoding, in these two parts. So these are the active research area if someone is interested in that. Now, whenever we talk about quantum computing, the first thing that comes into our mind is speed. Quantum computers are faster. We all know that. If we know quantum computing or not, we have some idea that, okay, this is a computer that is faster. Now let's address the elephant in the room, that is exponential parallelism. Just in the previous slide, I said that a bit can be in 0 and 1, 0 or 1. A qubit can be in a superposition of 0 and 1. That means at a time, it can do two things. That is parallelism. And quantum computers can give exponential speed up. So in our head, there is always a thing that if you're using a quantum algorithm, then it will give exponential parallelism. Now there is a catch. Just to remember you again, quantum computers can represent 2 to the power n steps simultaneously with n qubits. Simultaneously. So if there are 4 bits, 4 qubits, then 2 to the power 4 steps can be represented simultaneously. Now a 4 qubit system can be in a superposition of all 16 states at once. This sounds amazing, but whenever you are doing the measurement, this is a property of quantum mechanics, that whenever you are doing a measurement of a qubit, the superposition breaks, the state collapses. So you can never observe multiple states at once. Yes, there are multiple states stored, but what's the point if we can't observe them? Like what are the values? It is there, but if you can't see that, then there is no point. So you can never observe multiple states at once, because when you measure, you get one outcome. That is probabilistically. So the idea of that in this type of cases, quantum computers compute 2 to the power n values in parallel is kind of misleading. It can store 2 to the power n values, but for computing 2 to the power n values, there are other ways to do. It's not that straightforward. Now, classical systems, so classical machine learning or stuff, they use real probabilities, positive probabilities, right? Suppose cat dog classifier at the end, in the end of neural networks, we get some probabilities. Suppose 0.8 cat, 0.2 dog, then we'll say it's a cat. They give real positive probabilities. Now, quantum systems use complex amplitude. It's not real number, it's complex number. So that's mathematically different and it enables interference. Now this is again, I'm going to quantum mechanical properties. We will not get into a much of maths and physics in today's talk. But what I'm trying to give the idea is simply mapping a data into quantum space is not enough. True quantum advantage lies in exploring novel quantum feature maps and workflows that where classical computers genuinely struggle with. So first we have to take a problem in our hand which we cannot do or it will take a lot of time in classical computers. So classical computers were failing. In those cases we can try to solve it with quantum computers, and if we can, there lies the true quantum advantage. So what we have to keep in mind that quantum computers or quantum machine learnings are not automatically better. That's different. That thought process behind quantum computers or quantum machine learning is entirely different, and we need to use that difference strategically. Is there any question right till now? Otherwise, we will go to the next slide, that is why we are using quantum. Like it's not a talk about demotivating using quantum computers. I'm just trying to say that we must learn where to use and where not to use. There are a lot of places where to use. So there is a scientist Carlton Case, a famous quantum physicist. He once said that Hilbert space is a big space. Now, this simple statement captures the essence of quantum computers' potential power. So if you can look at the slide, the numbers in the slide, with 275 qubits, 275 is not a very huge number, right? With 275 qubits, we can represent 2 to the power 275 states. That's more states than the number of atoms in the observable universe. Now, let's think in for a moment. The exponential scaling of the quantum state space is the foundation of quantum computing's theoretical power. There's no doubt in that. But the reality check is we need to internalize that accessing that power is extraordinarily hard. Our current hardware, like current quantum computers available in the world, somewhere between hundreds to thousands qubit. Hundreds to thousands. But they are noisy. That means decoherence happens in microseconds. You set the qubit to some value, it decoheres and goes to 0 in microseconds. Qubit connectivity is limited. Like not all qubits are connected with each other, so you cannot do operations between all qubit at once. There are ways in which you can do, but again, those are complex. And there, so I will come to gate, I will come to circuit, but just to tell the essence I'm trying to tell is everything is very noisy. So while the Hilbert space is vast and theoretically powerful, the question we are exploring today in today's research domain is, can we navigate it effectively for machine learning tasks given the current hardware constraints? The hardware we have right now in our hand, using that, what we can do? Can we design algorithms that work despite that noise? Yes, we can, and that's what makes this field both exciting and challenging. And we'll see today how using these small, noisy, less connected quantum computers, we can do something meaningful. So we will go to introducing quantum to machine learning. How to introduce the quantum sense to machine learning. So whenever you see some QML talk, you can see this picture. This is a very famous picture cited. It is cited. It was a paper of QST from Maria. Now, we categorize quantum machine learning into 4 regimes based on the data type and algorithm type. What is data type? On the data on which we are acting. So, suppose we download some data from Kaggle. Is it a classical data or is it a quantum data? That is the data type. And there will be some algorithm type, like are we using normal SVM or normal neural networks or normal reinforcement learning? Then there are classical algorithms and there are some quantum version of those algorithms. So there are 4 permutation combination. One is classical data, classical algorithm. Of course, there is nothing quantum in it. Classical data, classical algorithm is our normal machine learning, what we usually do. Suppose support vector machine. Support vector machine doing image classification. That is the CC part. CQ is classical data quantum algorithm. Now this is the most important and interesting part today, because most of the research, it's not that the other 2 are useless, other 2 are more difficult to do, but the most research that happens nowadays, the kind of work we do, everything is in the CQ domain, where there is classical data, your applications, be it medical, be it mathematical, be it a graph problem. So classical data and quantum algorithms. So using some quantum algorithms, we will try to classify or any ML task of the classical data. So this is the most discussed QML research topic today. Yeah. And so our focus of today's talk will be on QC. We will get back to that. But other than that, sorry, CQ, we will get back to that. Other than that, there is QC, where there is quantum data and classical algorithm. For example, suppose you want to analyze quantum sensor data with classical tools. Then the data is coming from quantum sensors, so it will be a classical data. And you are doing something with the classical tool, so it will be a quantum data on classical tool. And the last part is fully quantum learning, that has data is quantum, learning is quantum. But for QQ or fully quantum learning, we need QRAM, we need fault tolerance, which we don't have yet. So for now, we are basically in the CQ regime. Now let me add one more important point before about the CQ regime before we move on. So in this regime, quantum data can mean different things depending on the context. It might refer to measurement outcomes from quantum experiments, because when we have a quantum experiment and we measure it, we get classical data. That's the quantum mechanical rule. Or it could mean quantum states prepared by another quantum circuit that serves as your input to your ML model. In future, it might mean data stored in quantum random access memory, that is QRAM, though it is still theoretical. So the key insight is most of the QML work today focus on the CQ regime. It applies quantum algorithms to classical data sets that have been encoded into quantum states. So we have classical data, we have to know how to convert it into quantum data, then feed into the algorithm. And we are not yet at the stage where we have large-scale quantum data sets natively. We don't have that much data. So we are taking classical problems that we have a lot, the data and the problems in our hand, and asking, can quantum processing helps here? Let's take a small detour, and in our head, we just revise what is the classical, how the classical method works, so that we can see the quantum version of it. So let's recap SVM support vector machine a little bit, because that will be the foundation. So suppose the goal is binary classification. With what it does an optimal hyperplane that maximizes the margin to the nearest data points. We call the nearest data points as support vectors. And we have these formulations, one primal formulations where fx equal to theta dot phi x plus b. It looks like our original line equation y equal to mx plus c because we draw the lines. And here theta are the parameters, phi x is the feature map. We need them all. When doing quantum, we will need these kind of things. That's why I'm discussing this. So there is one primal function, there will be one dual function. Now, just take a look about the dual function. So our primal function was fx. Now we are trying to see the dual function. In dual function, we introduce the thing k. The k was not explicitly mentioned in the primal. K is the inner product between feature vectors. Now, dual form basically enables this kernel trick that we need only inner products. So instead of doing explicit high dimensional vectors with their product, we are doing inner product. This basically makes quantum kernels possible. So quantum computers basically computes these inner products in exponentially large space. So how this works, like quantum kernels, how this works? There are some steps. The first step is we encode our data, that is suppose classical x as a quantum state phi x. It is in different kind of notation. You can see that one horizontal line and one angular bracket. We call this ket notation, K-E-T, ket notation. So we include, the first step will always be encoding our classical data x as a quantum state phi x using feature map circuit. So there will be a circuit which does the conversion. Step 2 will be, we will prepare two states. One is phi x and phi xi, and another will be phi xj. Step 3 will be, we will measure some overlap between this xi and xg. Step 4 will be, we will build an n cross n kernel matrix for all the pairwise overlaps. Now we will, when we will be doing the Qiskit hands-on, we will see basically why this overlap thing can go to a solution of while doing the classification. The fifth step will be training our normal classical support vector machine on this matrix. Now, one thing just I need to tell you that whenever we are doing quantum machine learning, at least in the CQ regime, these things are hybrid. That means some part will be done on a classical computer, some parts will be done on a quantum computer. It's not that the entire thing we take it and feed it in a quantum computers. No. There are some parts that has to be done on classical computers because classical computers are good for that. And the part where classical computer is not good at, those parts we will push to the quantum computers. So in this entire thing, the only quantum part is computing kernel. SVM training is classical. Okay. Now, where is the bottleneck? The bottleneck is, as I said, that you have to build n cross n kernel matrix. That means there are n square quantum circuits. So suppose we have 90 training examples. That is very low. In classical machine learning, we deal with more very large training samples. But suppose you have just 90 training samples. For that, you have 90 cross 90, that is 8,100 circuits. 8,100 circuits. Now, just assume that each circuit can take 4 seconds to run on a quantum hardware. That will take you 9 hours time. So this is the bottleneck. In classical also there is a training time bottleneck. Here also we have the bottleneck. So this big O of n square scaling basically limits quantum kernel to small data set. Now there are plenty of QML algorithms. quantum kernel is a very basic algorithm. Once we learn this, once we are habituated in this, we can go to more advanced algorithms, not for today, but to explore ourselves. That is good for larger data sets. But today we'll keep our main focus on quantum kernel methods because that is the basic thing to learn. We first have to learn the ABCDs of QML, then we can construct a paragraph. We will learn about other methods, but not in detail. And we will see this again in the live notebook when I'm showing that. The next approach is VQC. Now, this is a very powerful approach, different approach. So instead of fixed circuits, so in the previous slide, what I said that we have to make circuits. We have to make 90 circuits, 8100 circuits, n square circuits. Here, we won't make that many circuits. Instead, the circuits will be parameterized. That means in each of the circuits, there will be some parameter which we can change each time. What we change? We change the angle theta. So quantum qubits are basically, you change the angle and the qubit changes. So using this angle theta, we make the parameterized circuits. When you can use it, this VQC, firstly the VQC works very well in today's noisy small scale quantum hardwares. When we use it for classification, so VQC basically means variational quantum circuit. When you use for classification, it's again VQC, variational quantum classifiers. Sometimes we structure it exactly like classical neural network, then we call it quantum neural networks. So all things are VQC. Now VQC basically combines quantum circuits with tunable parameters, and it basically learns from the data. And they are more general than QNN because VQC doesn't mean, so QNN basically part of VQC. And we will start, before understanding VQC or quantum neural network, we will just show a small recap of classical neural network, and then we'll build the intuition that how can we impose quantum things into the classical neural network. There is nothing much to say about neural network, a normal neural network. It is a computational model. It is inspired on our brain structure, functions of neurons. There is one input layer, some hidden layer, some output layer, and between them there are connections, those activation functions, their biases, and weights of those links. Now, classical neural networks have layers of neurons with weights and biases trained via backpropagation. Okay. Now, if we see here, so classical neural network basically thrives on the probability. So suppose here you can see in the picture, we will get into that again, that if it with P0 probability it is a dog, with P1 probability it is a cat, and things like this. Now, about input layer, output layer, hidden layer, you all almost know. Input layer, we give some data that can be image, that can be pixels. Output layer, probability, like 90% dog, 50% cat, or something like that. There are hidden layers. Those are basically, they process the signals through weighted connections. Now, the core building block of a neural network is perceptron, the basic neural network model. So what does it compute? It computes y is equal to a function of wx plus p. Now, this function is called activation function, and this b is called bias. Now, there are non-linear activation functions like ReLU, sigmoid. Those are essential because without them, the network will collapse into a single linear transformation. Now, that why this non-linear thing I brought out, because this non-linearity is basically the essence of neural network, and this is inherently absent in quantum neural networks, and we have to bring it up somehow, this non-linearity thing. So linear layers, there are linear layers, like the last layer is usually ReLU or something like that. The previous layers are linear layers. Linear layers learn weight. But non-linear layers, the activation layers give flexibility to model complex patterns. So if you have to capture complex patterns, you need nonlinearity. So each of the connection between neuron has a weight and a bias, and these parameters can define how signals propagate across layers. There is a cost function that you know. At the end, we calculate that how accurate it is. There are many methods like this. Like here, I have mentioned the mean squared errors, where you have the true level, the predicted level. Suppose it should come 100% or 1, you get 80%, 0.8. You make the difference and do things like that. And depending on that cost, the network updates weights and biases to minimize this cost using classical optimizers. Like there are many classical optimizers. For example, we have gradient descent, where we have a plane like this where we want to find the global minimum. Now, quantum circuits are unitary and linear. The non-linearity part is not inherently present here. So, what is non-linearity? The classical activation functions. We don't have it here. So, through mimicking the neural network's expressive power, non-linearity you have to introduce separately. So, the common quantum approach includes we can use measurements. Now, measurement is a nonlinear step. We can do mid-circuit measurements. We are not getting into those details because those are mathematical, but just try to get the essence of what we can do to introduce non-linearity. There are things called partial measurement, mid-circuit measurements, and things like that. There are quantum Fourier transformation, those things. Those things basically enables the variational quantum classifiers or variational quantum circuits to act as the quantum analog of our neural networks. We have used many technical terms. We will try to see this with a picture. The picture may not be very good quality because some of the part are just handwritten, but we will try to understand what it is trying to say. So if you see the screenshot kind of thing, that is basically a normal classical model. Anywhere you can get this kind of pictures. You have a training data, you have a model, then you calculate the cost, then you calculate the gradient, you update the theta, go back to the model, again calculate the cost. This is your normal classical flowchart kind of thing. Now, when you are dealing with variational circuit, we do change into a small part. So we basically change the model part. The other parts remain same. I'm talking about now variational circuit. What do we do? Instead of this fx thing, we calculate, we take a state, quantum state psi. So psi is again inside that we are looking symbol, what we call as ket. And then we feed this psi into a circuit. That circuit is called variational circuit. Why variational? Because we are varying. What we are varying? We are varying the theta. So U theta. U is a gate, quantum gate. And we make U theta and we change this theta. So it becomes a variational circuit. Finally, we do a measurement. Why measurement? Because measurement introduced non-linearity as per the last slide. So we do this. Now, there are some more terminologies that will be beneficial to know, because after this talk, if you just read some article or something, just keep in mind that parameterized quantum circuit, ansatz, variational circuit, everything is same. Like these are different terms. That means U theta, where theta is changeable, where theta can vary. So parameterized quantum circuit, ansatz, variational circuit, all can denote this U theta. Okay. Now we will see a basic block diagram that how we can use this variational quantum circuit as a classifier. There are 4 steps. The first step is encode classical data to quantum data. This I already explained. We have classical data in our hand. We can't feed that to quantum computers. Quantum computers don't understand this. Like for normal computers, what we have to do? We have to convert it into binary. There are techniques for that. That is also called encoding. Here also we have to convert the classical to quantum. Then you applied the parameterized model, or which I also call ansatz or U theta. Then we measure the circuit. Always remember, in quantum, measurement is classical. How much quantum thing you have, once you measure it, you get a classical value. And once you measure it, there are tools and techniques to extract the labels. And then we have to use optimization techniques to update the parameters. Now, these optimization techniques, the optimization techniques we will discuss are all classical things. So there is no quantum part in the last two boxes. So this is a picture of quantum neural network. So here input data is encoded into a quantum state. How? By unitary layer U. There are W layers or weight layers corresponding to, again, parameterized quantum circuits where there are variational parameters. And there is the final measurement layer which extract classical information from the quantum state. So data encoding and the weight distribution, those are linear or unitary operations. Measurement layer introduces the non-linearity. So together they can mimic what happens in neural network. There are linear layer, non-linear layer. Linear layer for weight adjustment, non-linear layer for activation. This particular structure basically mimics that linear non-linear structure of a classical neural network. And at the end, a classical optimizer comes and tunes the circuit parameters by minimizing a chosen cost functions. So instead of ReLU, in classical we have non-linearity things like ReLU. Here, instead, we use measurement as a nonlinear step because we need nonlinear steps. Now, there is one powerful technique here that is called data re-uploading. So it basically re-encodes the same data between different variational layers. Why? Because it can capture a lot of things which is otherwise missed. That is called expressivity, how good you can learn. And even a single qubit can act as an universal classifier with repeated data loading. So it makes the size of our circuit smaller. Now there are some, I'm not getting into the details, but there are some papers by Perez Salinas 2020 paper where they have proven this thing. And VQC, this variational quantum classifier, scales with big O of n. We have already discussed that quantum kernel estimator big O of n square when we discussed that 90 into 90 8100 circuits. So quantum kernel estimation, the basic thing is big O of n square. This VQC scales as big O of n. So VQC is better in this sense, less number of circuits with more larger thing you can do this. But of course everything has their pros and cons. For VQC, there is a thing they suffer or disadvantage that is called barren plateau. Barren plateau means gradients vanish exponentially with circuit depth. So when you are increasing the circuit depths, the gradients are vanished. If the gradients are vanished, then suppose you are imagine you are trying to do something called gradient descent. If everything is flat, then you can't find the minima. That is the vanishing gradient problem or barren plateau problem. So it makes the training difficult. So of course there are always be some pros and cons. What we have to keep in mind, what is our application? Because different problems need different trade-offs. So now we have learned a lot of terms, lot of things like you can do quantum kernel estimation, variational quantum classifiers, neural networks, quantum neural networks. Now we'll come to the basics, how to do it. So first we will see some data encoding methods. We will try to see just one data encoding methods in depth, and we will learn the names of other data encoding methods so that when you are doing by yourself, you can use according to your need. So data encoding is the most critical part of quantum machine learning. This is how we bridge the gap between classical input data and quantum states. The encoding strategy you use that basically affects your algorithm's computational power. So people need to have some experience on how to use. So there are different data encoding, how to use or what to use. So data encoding and data loading is almost same, and it acts as a feature mapping from classical feature space to Hilbert space, quantum Hilbert space. Because in classical kernels, what we do, the classical kernels map to higher dimensions, things like this. So what is Qiskit? Qiskit is a software development kit from IBM via which you can run your circuits into quantum hardwares. There are other software development kits by other companies by which you can use their hardwares. So Qiskit is just a software development toolkit. It is written in Python. Like you just have to know Python to use Qiskit. Nowadays in C also it is coming. So Qiskit has different packages. Like in Python, we have different libraries, different packages to make our life easy. In Qiskit also, there are different packages to make our life easier. So there are built-in feature maps like Z feature map, ZZ feature map. They automatically extracts the feature for you. So this Z feature map, ZZ feature map, they use rotations. Rotation is a gate. Rotation and entanglement layer to expand data representation. Now, the key insight is encoding, data encoding directly affects the computational power of your QML algorithm. There are some algorithms which produce product state. They are easy to simulate classically. But then if you create something which is easy to simulate classically, like you can run on a simulator, then there is no point doing that in the research level, not for learning. While learning, we'll start from the very scratch or very small 5 qubit, 10 qubit. But if you do something in a research which you can simulate classically, then don't do it in quantum, do it in classical. Otherwise, we'll lose quantum advantage. Now, entangled encoding can capture some rich quantum correlations where the classical computers really struggle with. They can't do that much of complexity. But there is a trade-off that more entanglement will means higher expressivity. True. Expressivity means it can catch features from all of the aspects. It will not miss anything, but also deeper and noisier circuits. So while writing our own algorithms, we have to balance these two things, that encoding power and hardware constraints. So the takeaway is we choose or design encoding circuits that matches our choice, our data structure, our hardware limit, what we have in our hand, what is our problem statement. There is no one-size-fits-all solution for this. We will see some quick notation setup. So if we have a data set of m data vectors like capital X where x1, x2, dot xm is there, and each vector xj has n features, and we can refer a single data vectors as x. So what is the feature mapping notation? It is phi x. It's a general feature mapping which we use in machine learning. Here ux is the circuit-based implementation of a quantum feature map. So instead of phi x, we are using ux. U means unitary gate. X is the angle. So both represent mapping from classical data to quantum state, but here ux basically emphasizes the unitary nature of quantum operations. Now, this is a very important part of today's talk, that is normalization. In classical also we do normalization at times, but that is purely optional. We normalize to improve performance. If we don't normalize, it is not that everything will collapse. So a common approach is minimax normalization. But again, it is optional. You can run without normalization. In quantum computing, normalization is fundamental. It is not optional because according to the rule, every quantum state must satisfy that psi square should be 1. That is, what is a quantum state? How is a quantum state written? If psi is a quantum state, then it will be like alpha 0 plus beta 1. So with alpha square probability, it can be 0 while measuring, and with beta square probability, it can be 1 while measuring. The criteria is alpha square plus beta square has to be 1. So it can be 50-50, it can be 70-30, it can be 20-80, but it cannot be 50-52. So the square, the sum of the square should be 1. This basically ensured the measurement probabilities sum will be 1. This is a physical requirement. Now, what is the implication for encoding? So there are amplitude encoding that requires, so amplitude means these things, alpha square, beta square, those things are amplitude encoding. The summation will be 1. There are other criteria for phase encoding and stuff. We are not getting into those details. But quantum normalization basically defines how classical data must be rescaled before encoding into qubits. How? By normalization. Now we will see just one example of how you can do data encoding in hand. So let's start with a simple thing, basis encoding. It is also called digital encoding. The idea is we will encode a classical p-bit string, into a p-qubit computational basis data. So we have p-bits, we will convert it to p-qubits. This is the most basic thing. There is nothing much to understand. Suppose we have two classical data, x1 and x2. x1 means 0, 1. x2 is 1, 1. These are classical data. We want to feed it somewhere into the machine learning model. What will you do? You will make a quantum state 0, 1 and we will make another quantum state 1, 1. We just convert them normal state to quantum state. So this was like, if this is 0, 1, this becomes gate 0, 1, this is 1, 1, this becomes gate 1, 1. Let's see this same thing with some more examples so that the concept will be clear. Suppose we want to encode the number 5. This we always need. Suppose we have a problem in your hand, we have a data set, all the data are in classical model. We want to try running QML, be it a try problem, be it a research problem, we want to try QML, we want to run it. You have to convert it, right? You have to convert the data into quantum data. For that, this basis encoding is the easiest part. So convert 5. So first you convert into binary 0, 1, 0, 1. Then what I said, and convert the entire thing into qubit state. So now this is gate 0, 1, 0, 1. Now if you see it at the 4 qubit state, the first qubit is 0, second qubit is 1, third qubit is 0, fourth qubit is 1. So for multi-feature data, each feature is converted to binary, then assigned to a group of qubits depending on how long the group of qubits are. For example, if you have to encode 3 numbers, suppose it is a vector 5, 7, 0, then it is 0, 1, 0, 1, 7 is 0, 1, 1, 1, 0 is 0, 0, 0, 0, and you get a full 12 qubit basis stacks, where first 4 qubits is for feature 1, second 4 is for feature 2, last 4 for feature 3. So you can understand that this is very basic, simple to do, but this is qubit expensive. Like whenever we are doing anything, so your feature grows, your qubit size grows. Now when your qubit size grows, that means you need larger machines. This will be the last slide for basis encoding. Here we will see how encoding we can do and how it looks like. So this is basically the Qiskit code. Here we convert each feature to a 4-bit binary number. That is easy to do. Like everything is in Python. In Qiskit, you will not see any different syntax or something like that. So what we do, to create a circuit, this is the package. So in Python, you have to install Qiskit, pip install Qiskit. Then you have to import this quantum circuit package. And you have three data points to encode, right? X equal to 5, Y equal to 7, Z equal to 0. These are the basic commands, like there is nothing quantum in this. Basic commands to convert an integer to binary in a 4-bit size. So you get your X bits that will be 0, 1, 0, 1, Y will be 0, 1, 1, 1, and Z bits will be 0, 0, 0, 0. Then you combine all. So you get the list of all 12 bits. Now you know it 12. So this is manually we can just create a quantum circuit of 12 qubits. Then what we do? This is the thing, when we create a quantum circuit, all are initialized to 0 by default. But you know where the ones are? Second, fourth, sixth, seventh. In those places, so where there is some 1, if bit equal to 1, we put a X gate. That means X gate is not kind of NOT gate. X gate is NOT gate of quantum. X gate means 0 to 1, 1 to 0 in qubits. So we put a X gate there. Now you can see the circuit, right? In the circuit you can see there are 12 qubits and there are some X gate where it should be 1. This is a very basic way to do basis encoding. There are other encodings. I am not getting into the details of other encodings. I will share the slides, and if needed, you can go through this. But this is a little better encoding, amplitude encoding. And apart from amplitude encoding, there will be angle encoding. I'm just skipping these parts because we can't cover everything today. There are phase encodings. And these are basically some difference between different kind of encodings. There are higher order encodings. And so this thing again we want. This thing will be needed to kickstart the QML journey. So Qiskit provides several standard feature maps we have already discussed. These are very important. Which feature map to use? You will understand while doing it slowly that, okay, this is working for my thing. This is working for my hardware. This is not working. Let's change it. So there can be Z feature map. It is shallow circuit. There is no entanglement. It is good for small data set and small scale devices. So if your problem statement is small, use Z feature maps. There are ZZ feature maps. Now Z feature maps means there is a Z gate. ZZ feature maps means there is something called RGZ gate that is applied. Where it is used in quantum support vector machine, quantum kernel trainings and things like that. There are Pauli feature map, efficient SU2. While doing the works, we basically understand what we should use for our thing. Now we'll move to the next section where we basically apply a variational model. So we have encoded our data, right? The first step was encode the data that we have done. Next step will be we need a parameterized quantum circuit with tunable parameters theta that we will learn to classify. Again, we will not get into the very much mathematical details, but we will try to understand the structure. So this encoding data part is done. You had the data, we encode that. Now how to design this? Now how to design this is an open problem. Like there is no rule that, okay, this is the best answers. This is the best circuit. So this is one of the hardest open problem in QML. Most of the good research that is happening, that is some is encoding data, but the most complex research are going in how to design the answers, how to design these parameterized circuits. Of course, it is problem dependent and it requires a lot of experimentations. But the goal should be, there are two things to keep in mind. One is expressibility, means can this circuit represent enough quantum states to learn complex patterns? Can it explore the Hilbert space effectively? And another is trainability. Can we optimize it without hitting the Bain plateau? Can we optimize it without the vanishing gradient problem? Is it shallow enough? Because if it is deep enough, then there is a lot of noise and our thing collapses. So these two goals are contradictory. So we have to find a sweet spot. So more expressive circuits tend to be deeper with more entangling gates. That means more noise, higher risk of barren plateau. Shallow circuits are very good trainable, but they might lack representational power. So finding the right balance is basically an active research area. Now, I am not getting into the details of those kind of research, but if someone is interested, uh, how to uh, how to balance between the expressibility and trainability, you can look. I will share the slides at the end of the talk, but you can go through this paper. This is a very good paper which basically discuss why this good best expressibility is not a good thing always, or best trainability is not a good thing always, and they have did a lot of experiments to show how a better ansatz can be designed. Anyway, leave aside, what will be our practical strategy for ansatz design? We will start shallow. We will start with 2-3 layers or 1-2 layers. If the performance is very bad, we will add layers gradually. We will not start with a very deep layers. We will just hit with noise and we will get garbage values. We will use hardware efficient gate. What is hardware efficient gate? So suppose you are using a particular quantum hardware from a particular company, your device will have some hardware set, gate set. If your friend is using another quantum device from another company, he will have another gate set. So you have to first know what is the basis gate set of your hardware and act accordingly. Use those kind of gates. It will be better for you. Then I at the very beginning I said that not all qubits are connected with each other. And if there is no connection between two qubits, you cannot do this kind of, I have drawn this kind of connection, there is a connection, there is a connection. This you cannot do. So you have to keep in mind where to place the qubits so that you can do those things. So a lot of things to keep in mind for a good ansatz design. Later we have to benchmark and iterate. We have to test on small data set first. We have to measure the training loss. Then we have to go back again and again. So this is an iterative thing, the ansatz design. This is the most difficult thing for QML and it is the iterative thing. It is not an one-shot thing. So to summarize, ansatz design basically balances the expressibility, that is, can it learn, with trainability, that is, can we optimize it? These things are balanced. We will use hardware efficient gates, we will respect the connectivity, we will start shallow, and we will iterate on performance. This thing has to keep in mind. That's not the last part, basically the second last part of the circuit is extracting label. So we have run our quantum circuit, right? The quantum part is done. Now again, come back to classical. We need to measure and convert our quantum measurements outcomes into classical predictions. Now, once we have encoded the data, UX part, and applied the variational model, the W theta part, we have evolved our quantum states to some psi. Now we measure. Once we measure, it collapses. It collapses to a state probabilistically. So suppose our measuring is give us outcome get I with a probability alpha I square. Now we can run the circuit many times. We can usually run 1,000 or 10,000 shots and we collect a statistics. Okay, out of 1,000 times, suppose 900 time it came this and 100 time it came something garbage. So from this measurement counts, we extract a classical prediction, that is our class level. This is almost like what we do in normal classical machine learning also. There are two common strategies. One is, again, for today, we don't need to get into the details of that, but it's better if you just know the names and go through this later. So one is parity post-processing. What it does, it measures all the qubits. It computes the parity. And it is a single, and there is one thing called single qubit measurement. So if it is a circuit, if there are multiple qubits, you don't need to measure all the qubits. You can just measure a single qubit. So there are two techniques. One is parity post-processing and another is single qubit measurement. these things I'm skipping a bit for now. Just to start with, we don't need really to get into the very details of mathematical models. To start with, we can use the packages to do it, and later get into the depth. Okay, what is happening inside the package, because we already understood in depth how this ux work and this w theta works. So the quantum part we already understood. These things we can see later. So let's skip these parts and go to some more interesting parts. So these are the extract level things. The last part is more easy to understand, that is optimization. So we have a cost function, C theta, that basically measures the prediction error, that this should be the case, but we are getting this. Now we need to find parameters theta that minimizes it. It is the same as classical thing. Now this is where the gradient descent and parameter shift rule comes in. So we need to optimize our variational circuit. We already have trainable parameters theta. Now we need to update these parameters to minimize our cost function. So the standard approach is gradient descent. We start with the random theta. We calculate the cost function. We compute the gradient descent, that is the derivative, delta c delta theta. We calculate the derivative and update the new theta, like theta new equal to theta old minus learning rate into the derivation. It's similar like the classical things. Now, quantum circuits are not differentiable like classical neural networks. In classical neural networks, we do this del c by del theta thing. In quantum neural networks, these are not differentiable. So in PyTorch or TensorFlow, there are differentiation functions. We cannot do that here. So how do you compute that? For that, there are different optimization methods. Today we will just listen to the names. So there are gradient based methods, that is parameter shift rule. There are gradient free methods, like these are more popular, the gradient free methods like Kobila, SPSA. So when we start, we usually use Kobila as our optimizer. They don't need gradients at all. This is the parameter shift rule. Again, I'm skipping this for now. And come to the most important question with which we started the thing, that is quantum machine learning actually advantageous? So where it works and where it doesn't. So let's take a step back and revisit the data encoding again. Suppose we have a classical data, 2D data, and if we want to encode this data into a quantum state, we need n qubits. Now you are encoding this data into a state phi x, written as a vector of 2 to the power n entries. Now if 2 qubit, there are 4 entries. So you are mapping something into a higher dimensional space. Now you can find the similarity with feature map in normal SVM. So the most important part lies in the feature map. So it will be advantageous if you can correctly extract the features, and if you can correctly convert the classical data into quantum data. So it always depends on the data and the model. Just a little bit of recap what we are doing for a QML. We first have to do the data encoding. For that, there are multiple methods. Today we saw the basis encoding part mainly. Then we have variational models, that is the circuit, where there are angles theta that can be changed, and finally there are optimizations. Now again we will come to this question, where should we use and where should we not? So most of the classical dataset we use today for QML, no, we should not use for research problem. Again, I mentioned this again and again, for research problems, no. When a student or a faculty is starting his or her journey in QML, Of course, we will start with small data set. Of course, we will start with those image thing, those straight line or curve. Is it five, written 5 or 7? Is it's a cat or dog? Those kind of things. But those cannot be a research problem. Those are good for you to practice, to try to play your hands with QML. Why? Because classical machine learning is faster, more accurate, runs on hardware you already have, like your laptop. Quantum computers are noisy, slow, expensive to access, and you need special datasets and problem structures to see quantum advantage. Now, then where should we use QML? That is the most important part, because till now I have discussed where we should not use. That is the basic ML task we should not use. Why should you use? Any classically hard problems, NP hard problems. Problems where we have theoretical guarantees that quantum is faster and classical is slower. For example, there is a Nature paper of 2021 by Liu from IBM Quantum. They demonstrated quantum speed up for supervised learning based on discrete logarithms. They have proved that this is classically intractable but quantumly easy using source algorithm components. This is one thing. Other thing is there can be some data that are quantum native. Suppose the data is coming from quantum sensors. A data is coming from quantum simulation data. Some quantum chemistry calculations. Those data are inherently quantum. Their QML will work good. Their ML will not work good because that vast kind of thing an ML cannot capture. All essence of it, ML cannot capture. Where we can use, apart from this, research and development algorithms. You are trying to make a quantum algorithm. You are trying to design something. You are trying to benchmark something. Then it is valuable even if your current QML result does not beat classical results. So it's a negative result. Suppose your classical algorithm gives you 95% accuracy. You make a new quantum algorithm which gives you 94% accuracy. But this is valuable in research because you are making some good quantum algorithms. Maybe for particular dataset it is giving less accuracy, but for other things it can be good. So it is a good exploration. And why we should not use, I already said, don't use it for research purpose to classify horizontal vertical lines. You can do that in milliseconds in classical. If you run it in quantum hardware, it will just take you hours because there is so much queue while running a quantum system. Don't use it. For students, it's okay. For a college project, it's okay. It's not okay for a conference or journal to do MNIST classification, ImageNet data, those kind of things. If it is not doable in classical, it is giving bad result in classical. That means it is so complex that classical ML cannot do, then of course use QML. Of course use. Don't use QML if you don't have quantum resources. Suppose your problem needs 100 qubits. This is an hypothetical scenario because it's nowadays it is everyone can have 100 plus qubits for free. But just imagine that your problem needs 100 qubits, you have access to 50 qubits. Then there is no point in doing QML. And the production requirements. So nowadays, the quantum computers, there are research tools for now, not production systems. So there will be some uptime, there will be some latencies, there will be some delays. Those things also we have to keep in the mind. Now we will go to a little, we have little time, like 10 minutes or more. We will go to a web page and see how we can start running our Qiskit code for QML. Before that, to run our first QML code, we basically need 4 steps. What are the 4 steps? First, we will map the classical problem into a quantum problem. Then we will optimize the problem for our hardware. Then we will execute it in Qiskit runtime primitive, what is executing, running it in actual quantum hardware, and finally some analyzing and post-processing. And what we will do, we will go to this notebook. I will show you here. We will go to this notebook and we will see how the all the things we discussed, how to do this, like how classical data becomes quantum. We will take some data points, we will encode them, we will measure the overlap, and this overlap will basically tell you the quantum similarity, that is the building block for a QML. Before jumping into the code, just a few things I want to touch. We have to import some libraries like parameter vector, quantum circuits. These are basically building blocks for Qiskit. We need this imports called unitary overlap. This will help provide a circuit which computes the overlap between two unitaries. It basically says two states how close they are or how similar they are. And we need state vector sampler. It's a Qiskit primitive that simulates the state vector for a circuit and gives us some measurement. And of course, we need dataset. We will download that dataset. There are commands like wget for Windows, curl for Mac. And here we have downloaded this CSV file. And then as we do like xtrain, xtest, those kind of things. So what we actually do in normal classical machine learning that we will do, we will load the dataset. And finally, we build the feature map. For building feature maps, there are functions. We will use those functions. And after that, we will build the circuit, like the parameterized circuit, we will build the circuits. And finally, we will assign the parameters, like assign the theta values. There are some functions for visualizing, okay, what is happening after running that. So that's why we need this measure all and draw kind of things. And at the end step is we run it on a real hardware, or we can run it in a simulator. It is always advisable that before going to a real hardware, you run it in a simulator, see there is no error, then run on a real hardware. Otherwise, so for real hardware, you get, for IBM quantum hardware, you get 10 minutes free per month. Now 10 minutes is a huge thing. People sometimes look at 10 minutes per month, it's nothing. It's not like that. Like for me, when I did my PhD, entire PhD was done, like every month I used to get 10 minutes quantum time. That was enough for all of my PhD work to run every month. So suppose I start on 1st January, when I'm in 31st January, I will see, okay, 9 minutes and 55 seconds are utilized, 5 seconds left, and tomorrow I will get again 10 minutes, like this. So 10 minutes is huge for students and stuff. It's not huge for commercial purpose or hardcore research, but to start with, 10 minutes are huge. But the thing is, first run in simulator. If there is no issue, then run on a real hardware. And once this is done, you run the circuit, you get counts. That means how many times you get this, how many times you get this. We calculate the probabilities. We do the final post-processing. And finally, you get some result that this is happening. So we'll see the notebook at the last, because notebook you can run, like you can just go home and you can run things. I will see if I need to mention anything else. Okay, now let's go to the notebook. Before that, I will go to the notebook, but firstly I want to take any Q&A if there is any question, and scan this. Now I'm not sure if scanning this will work, because the QR doesn't work always. There is the Google Drive link. In this Google Drive link, you will get this slide, and in the slide you will get the link of the notebooks. So you can click a picture of this link at least. uh, so that you can get access of the slides. And while opening the notebook, I can take any questions if there is any.
Thank you, ma'am, for your valuable speech. Uh, Shankar sir, if there is any question, please ask to the ma'am.
Okay, thank you, madam. This was a very great session, and madam has already discussed about the classical versus quantum computations, or say quantum machine learning. What are the differences? How to transitions from the classical to quantum ML, and the suitability, that means the applications where it should be, where the classical environment is suitable, where the quantum environment is suitable. Madam has also discussed about the data encoding part, variational models, optimizations. Madam has also discussed about the virtual environment, particularly the simulator. So before going to formally conclude, let take some questions from the participant.
Okay, let me just show you this thing. So whenever you're trying to start doing code, you can go to quantum.cloud.ibm.com. Inside there will be learning tab. In the learning tab, there will be plenty of course. You can go to the quantum machine learning course, and inside that you will get these lessons, introduction, classical machine learning review, data encoding, quantum kernels, QVC and QNN. And then there is an exam. Everything is free. So you can try to do this course. I have covered a little bit of everything, but of course there are more details. And what I will just try, you everyone go home and run is, you can run this code. Everything is given, right? If you run this code, at least your computer will be set up. If you want to work in this, of course, only then. At least your computer will be set up to run this kind of things. So what we do, what I just said, that we import these libraries and then we map the classical problems to a quantum problem, that is a step one. We download the data set, we import the normal Python stuffs, then we convert, that get training data is converting the graph, that is a classical data set, into X-train, X-test kind of things. We prepare our kernel map, we build our feature map. Now, as it is mentioned that this could be pre-built feature maps like ZZ feature maps. Here we have used a very basic custom feature maps. Then you take two data points like x1 equal to 14, x2 equal to 19. So two data points, and we will assign the features to the circuit as parameters. The next point was optimize the problem for quantum execution. So once you have a circuit, you can't directly run it to a quantum hardware. You have to do some pre-processing steps for that. That is not mandatory, but if you do that, then your circuit running will be less noisy and faster. The step 3 will be the actual running, that run into the quantum hardware. You fix the number of shots, how many times you want to run it, you get the counts, and you finally analyze and post-process. This is a very basic, like very low-level code, but it is a good point to start with, and you finally get the result. Now this 0.8199 is basically how similar are they? Like the 14th data point and the 19th data point, how similar are they? That is the thing. So this was the very basic thing, but later you can go to quantum kernels. You will get codes to run quantum kernel. You can go to this QVC and QNN, and you will get code to learn this QVC and QNN. That's what I wanted to show you.
So, madam, can we take the questions?
Yes, sure.
Okay. The first question, that is, explain how quantum kernels in support vector machines can potentially provide exponential speedups over classical kernels for certain data sets.
So it will depend on the data set. That's what I was explaining. that quantum kernels inherently gives the parallelism, the exponential speedups, because you have n qubits and you can simultaneously store 2 to the power n things. We have seen how these things work, but you have mentioned the data set. On your data set, if it will work or not, that you have to see, is the data set is like that where you need exponential speedup. If you don't need that, if you want to try that, so there is a data set where you don't need exponential speedup. If you want to do exponential speedup in that, you will lose some speedup because for quantum you have to wait in queues and stuff like that. Does that answer your question?
Okay, actually this question has been asked by one of our participants. Okay.
Oh, okay.
There is another question. Probably you have already discussed these things. That is there any virtual platform available for quantum implementations?
So by virtual means, like you want, of course, like we can't go to near a quantum computer and code. So there is this IBM quantum platform. There are other companies quantum computers also, but I'm only discussing the IBM quantum platform because these are free to use. So what you have to do, you have to take a Gmail account or something. You have to open an account, and there you will get 10 minutes free per month. So what you have to do, you have to create a circuit using Qiskit. Qiskit is a language, and you can run it. That is virtual, of course, like not virtual, like it is remote. It is based on cloud. And before running into the actual hardware, you can run it in simulator. Simulator is
Simulator.
basically a
Okay.
classical thing, but it acts like a quantum computer.
There is another question which is related to the earlier one, that how are the companies like IBM, Google and startups contributing to QML development?
So for QML development, there are two parts. One is the algorithm development, where the software developers are working on, and the main hurdle is not the software part, that is the hardware part. So the focus is on to bring more and more qubits and the fault tolerance. So according to IBM's goal is in the roadmap, the fault tolerance was in 2029. So within 2029, the size of the quantum computers will be this large that we can guarantee fault tolerance, because for fault tolerance you need quantum error correction. For quantum error correction, for 1 qubit to correct errors of 1 qubit, you need multiple qubits. So it's a huge system, and to get to that huge system, the timeline for IBM quantum is 2029. Once this achieves, of course QML will speed up because we have the algorithms in our hand. The software side is more advanced, but we have to scale up the hardware side.
Okay.
So Google, IBM, everyone is now trying to build larger quantum systems and heading towards fault tolerance.
Okay, there is another question, madam, that is how the conventional computer differ from quantum computer in terms of hardware implementations?
Totally different. Like there is actually no similarity. Normal computers works in voltage, right? Like if we just break it down, it is 0 volt or 5 volt. 0 volt means 0, 5 volt means 1. I'm just not getting into the exacts, but the basics. In quantum, it is electron spin. So in classical computers, we don't deal with electron spins, right? So in quantum, the qubits are electron spins. Electrons can be spin left or right, top or bottom. So if it is spins is left, it is 0. If it is right, it is 1. And it is totally dependent on quantum mechanical property, not the normal physics properties. So the structure is totally different.
Another question that is a little bit different from this particular topic, that is it has been told that the conventional cryptographic algorithms will be obsolete on introductions of quantum computing.
Yeah, so there are two things. So many years back, Shor devised Shor algorithm, and once Shor algorithm come, he showed that Shor algorithm can break the very famous RSA crypto system, Now RSA crypto system is used in our banks and ATMs and everywhere. So of course, when if SHOR algorithm is here, then RSA is gone. But the good and bad thing is we don't have quantum computers which can implement SHOR. So SHOR is in pen and paper. To implement SHOR algorithm, we need very large quantum computers, which we don't have. So for now, RSA is secured. But what will happen when after a few years, large computers will come, SHOR can be implemented, RSA will be broken. True, that is proven. But there are two ways to deal with it. One is there are quantum cryptography things, quantum key distribution, QKD. That is one way of research. Another way of research is post-quantum cryptography or PQC, which is classical method. So instead of RSA, there are researchers are working on things, researchers are working on algorithms which cannot be broken by SHOR or anything like that, even if the big quantum computers come. So these are the two ways. Yes, RSA won't work when big quantum computers will come, but there are ways like either QKD or PQC.
Okay, thank you, madam. On behalf of the organizing committee and CS, I sincerely thank you again. I think particularly as this is a very emergent field, so the faculty members, the faculties who are already doing research in this particular field or planning to do research in this particular field will be very much helpful from this particular lecture. I also thank the audience for their active participations and thoughtful attention throughout the sessions. I once again extend our heartfelt gratitude to the speaker for making the session meaningful and memorable. Thank you, madam.
Thank you. Thank you, everyone.